So, just to recapitulate what we did in the last class, we say now that the symmetry elements are associated with a point or axis and or planes. So, the ones which are associated with the axis we have shown are limited to 1, 2, 3, 4 and 6 in case there is periodicity. That means, in case of crystalline materials we do have only these axes that are present. We of course have a mirror plane which could be along different directions, mirror plane perpendicular to an axis, mirror plane along a given direction and so on. We will bring in the issue of various orientations of the planes, but the operation is just that of a mirror plane. So, there is only one symmetry element that will come, which is the mirror plane. As far as axes are concerned, we get 2, 3, 4 and 6, and as far as the inversion center is concerned, we get this so called one bar symmetry. The next slide I am going to illustrate how these now become point groups and how many such point groups we can generate. So, the first set of axes we will consider are the limited to the 1, 2, 3, 4 and 6 because it is a periodic lattice, and these 1, 2, 3, 4, 6 are referred to as proper axes because they represent, if you recollect again the previous classes, they represent direct congruence objects. So, whenever these operations are there 1, 2, 3, 4 and 6, they represent the direct congruence objects. So, objects of direct congruence only will be corresponding to these proper axis systems. So, we can have a 1, 2, 3, 4 and 6. So, a total number of 5 such proper axis alone point groups that we will generate in a given crystal system. So, in crystals with or without translational symmetry, as we pointed out so far, operations may coexist. See, if there is no translational symmetry, like in the case of a 2, 1 screw axis, we have a translation symmetry. So, if there is no translation symmetry that is present, like in the case of a operation like the inversion center, then we can combine the 1 with the inversion center, which will give us the so called 1 bar. What now happens is that the object which is at x, y, z goes to minus x, minus y, minus z. That means, there is an inversion axis that is present. The moment we have an inversion axis, if you recollect the previous classes, we have objects which are present with this improper axis being present. These objects will be of opposite congruence. So, they will be of opposite congruence. That means to say that we can have therefore, the value of this angle between the two directions which we defined being negative. So, the improper axis therefore now represent the combination of a proper axis with an improper axis which happens to be the inversion center. So, if we now combine a twofold proper axis with an inversion center, we will get a mirror. So, we will work out how this happens below here, and now we will do the operation of a twofold which will give us x, y, z, which goes over to minus x, y, minus z, assuming that our twofold axis is along the y direction. Okay. So, the value of x and z now became minus x minus z. This is the twofold operation and this is a proper axis operation. So, the symmetry that is defining now the point group symmetry is 2. We take x, y, z to minus x, y, minus z. In case we have a 2 bar symmetry, that means we operate a twofold, and that twofold operation will now undergo a center of symmetry inversion. So, there is an inversion center which now therefore, x, y, z is no longer staying at minus x, y, minus z, but it goes to its corresponding inversion center operation. That means, x goes to x, minus x goes to a value of x, y becomes minus y and z becomes as such z. So, minus z becomes z, minus x becomes x. Now, this operation therefore is the operation of a 1 bar symmetry, because we have taken this value of x, y, z which is now x bar, y, z bar, and we have operated the center of symmetry to go to x y bar z. So, the so called equivalent positions with this improper axis operation are x y z and x y bar z. Examine these two carefully. If you examine these two carefully, it means to say that you have a mirror plane now and there is a reflection across the y direction. So, if the axis was coming perpendicular to the board, if the axis was coming perpendicular to the board, the plane of symmetry is with the board. And so, we have a point x y z which is above the board, now we will go below the board x y bar z, and therefore, this now is referred to as a mirror symmetry operation. So, what we therefore see is that 2 bar now gets represented as equal to a mirror. So, we have 1 which is a proper axis, 1 bar is an improper axis, 2 is a proper axis, 2 bar which is a mirror is an improper axis. Now, we have to consider the issue that we can since the operation is about a point, you see this is referred to as the point groups. So, the operation is about a given point and this particular point is identified with respect to x y z. So, the point we have identified is x y z. The space in which this object which is identified as x y z is located is governed by this particular symmetry. So, if the symmetry is 2, we will get x y z equals x bar y bar z bar. If the symmetry is that of a mirror symmetry, we get x y z is x minus y minus z and nothing else. It is a point group because of the fact that if we operate the mirror symmetry again, we will get back x y z. If we operate the two-fold axis again, we will get x y z, and therefore, we now define these as point groups. So, 1, 2, 3, 4 and 6 which are the proper axis define 5 point groups. There are total of 32. So, 5 of these are now accounted for. Similarly, the improper axis combination with 1, 2, 3 and 4 will give rise to these combinations and these combinations will add another 5. So, totally it has now become 10. We should also realize that since the operations do not involve translational periodicity, both these operations, the proper axis operation and the improper axis operation, proper axis is 1, 2, 3, 4, 6 and the improper one is the 1 bar symmetry, the inversion center. These two operations do not involve any translational component like we have in the case of a screw or a glide plane, and therefore, these now can be combined with each other. So, when we combine for example 1 and 1 bar, we can show that it turns out to be equal to 1 bar only. So, there is nothing new which will get created. In other words, the presence of the improper axis remains the same, whether you combine it with 1 and make it 1 and 1 bar simultaneously operating, you will get 1 bar only. Similarly, 2 and 2 bar now will introduce a combination of the proper axis twofold followed by a mirror symmetry. Now, what happens to the equivalent points? The equivalent points now will change. I will show you in a minute how it will change. The equivalent points will change. So, what happens is now x y z we are now considering the symmetry operation 2 by m. Okay. So, we are considering this operation 2 by m. So, there is a twofold symmetry and there is a mirror perpendicular to the twofold symmetry. So, this is a different operation than just a mirror or just a twofold axis. So, this is an additional symmetry, additional point group symmetry which is illustrated. So, this now becomes a new point group where what happens is that x y z will now go over to, first there is a twofold operation which will take it to minus x y minus z. Then on the x y z we will also operate a mirror symmetry. So, it becomes x y bar z. So, we call minus y as y bar, and then we operate on this the inversion center. So, we operated the twofold axis, we operated the mirror. Now, we can operate the inversion center. Inversion center is also operated on the original x y z. So, you will get minus x minus y minus z. So, the number of equivalent points has doubled. In case of the twofold axis, there were only x y z and x bar y z bar. In case of the mirror plane, it was x y z and x y bar z. Those were the two equivalent points. Now the operation 2 by m, that by m means that 2 is the twofold axis, let us say about the y axis, about the y direction. The mirror plane is perpendicular to the y direction. So 2 by m therefore defines a new point group, because the number of equivalent points now become 4 instead of 2, and this represents a different kind of space altogether, the 3-dimensional space. So in 3-dimensional space therefore, or even in 2 dimensions for that matter, this becomes a new point group symmetry. So remember, whether we are now talking about 2 dimensions or 3 dimensions, it does not matter, because the operation is about a point. This point is located in space. The space could be 2-dimensional, 3-dimensional, or a multi-dimensional. It does not matter, because we are now considering only the point on which the operation is being performed. And we have 3 coordinates x, y and z which identify that particular point, and that particular point now goes through these operations of twofold followed by mirror, and the combination of twofold and mirror giving rise to the center of symmetry. This x, y, z and x bar, y bar, z bar are equivalent points of a center of symmetry, or we can in fact better define it as an inversion center. This means that this particular point group has an inversion center in addition to the presence of twofold and mirror. Please note this statement, that in addition to the presence of twofold and mirror, it will also have a center of inversion. In this particular case, there was a center of inversion only, and that center of inversion insisted that the twofold went into a mirror symmetry. In the case of 3 bar there, however, it is different, because the 3 bar is an operation which goes first the threefold operates and then followed by an inversion center. I am not going to write down the equivalent points, but I suggest that you work out the equivalent points and find out how the 3 bar now is different, because we first operate 3 and then a 1 bar symmetry. Likewise, the 4 bar is similar to 2 bar, but we will have to find out in this particular case there is no separate operation like 3 and 1 bar. In 6 bar there is a separate operation like 3 divided by m. That means threefold symmetry for which there is a perpendicular mirror, and that results in a 6 bar symmetry. So some of these things can be worked out by looking at various kinds of pictures or diagrams, or looking at structures which go into these kind of point group symmetries. We shall do that in a later time when we actually look at molecules and relating the molecules to the space group and so on, in which it crystallizes. It's a little premature to discuss those issues right now. So we will restrict ourselves to the combination of proper and improper axes. So 3 and 3 bar is not going to give us any new point group. However, 4 and 4 bar, 6 and 6 bar will give rise to 2 different point groups, 4 by m and 6 by m. So we cut off these 2 fellows. These 2 fellows are one and the same, 3 3 bar equals 3 bar and 1 1 bar is 1 bar. So we generate 3 new additional point group symmetries, and therefore we have 5 plus 5 plus 3, total 13 point group symmetries, which are single rotation axis operations. We have considered only 1, 2, 3, 4 and 6. And in 3-dimensional space, it is not necessary that we should have only one axis. We can have more than one axis, and they can intersect at a point. So the point group symmetry is associated with the point. So at that particular point, it is not necessary that we should have a single axis of symmetry. We can have more than one axis of symmetry. One axis could be twofold, another axis could be threefold, and so on. One axis could be twofold, another axis could be a mirror. Now the mirror is not perpendicular to that axis, but the mirror is with respect to some oriented direction, which is different from the original twofold rotation. So effectively what we can say is, look at this particular diagram. This particular construction is referred to as the Euler's construction in mathematics. So suppose you take a point P, and then there is a point O about which we now consider the presence of combination of symmetry axis. So right now we looked at the combination, no combinations, we looked at independent individual rotation axis. Now we look at combination of symmetry axis. So if we look at combination of symmetry axis, suppose let us say there is a point P. Now it sees this rotation axis. This rotation axis now is centered at O, and that rotation axis, let us say, is a twofold axis. That means if P represents x, y, z, Q will represent, assuming that this is the y direction. It could be any direction for that matter, but assuming it is y direction, we will have x, y bar, z, x bar, y, z bar as the position Q. Now, the position Q may look at another possible rotation axis, and that particular rotation axis is represented by L2. L1 and L2 are the two rotation axes. So, then Q will go to R by that particular symmetry operation. It could be any of these. It could be a 2-fold, it could be a 3-fold, it could be a 4-fold, 6-fold, and such combinations. We will see how many such combinations are there, as a matter of fact, in a minute from now. So, when we do this operation, then Euler's theorem states that if you have one operation which is taking the rotation from P to Q and another operation Q to R, operating both at the same point O, then with respect to this point O, there will be a third axis which will take R to back onto P in order to define a point group. Remember, the point group definition is that we have to get back to the original. If we have a x, y, z, we have an x, y bar z, then operation of the mirror symmetry will bring the x, y bar z onto x, y, z. So, that definition is very crucial. So, keeping the same idea in mind, if we have a point in space about which there is intersection of more than one symmetry axis, invariably the third symmetry axis is invoked automatically, and therefore, we should have 3 symmetry axes. Now, because of the fact that we have 2, 3, 4 and 6, we have to consider all combinations of these, and when we consider the combinations of these, it will end up giving us the angle between these two axes, and that is what is given in this particular table. So, this particular table tells us that if there is a intersection of 3 two-fold axes, 2, 2, 2 for example, one two-fold axis going along the direction L1, another two-fold axis going along L2, then invariably I should be drawing it. I will draw and show you in a second. It should be an axis which will go here such that now R gets related to P by another two-fold axis. Okay. So, R and P now get related to each other by another two-fold axis, and that is the point which we have to think of and we should remember. So, whenever there are two rotation axes intersecting at a point, a third rotation axis is automatically generated. Because of the fact that we can have proper axis, improper axis and proper improper combined for a given direction of axis. So, this particular axis may be a proper axis, it may be an improper axis, it may be a combination of proper and improper axis. So, all these we have to consider. So, considering these, we now look at only the proper axis combinations in this particular table below. When we have only proper axis, for example, a proper axis rotation and a second proper axis rotation will never give the third one as an improper axis rotation. This is the extension of the Euler theorem. See, Euler theorem originally stated that if you have a rotation axis, P goes to Q and Q goes to R in another rotation axis, a third rotation axis gets created. That is the first part of the Euler's theorem. The second theorem is that when we have this as a proper axis, the L1 is proper, L2 is proper, then L3 has to be proper. It cannot be an improper axis. If there is an improper axis, we will see what are the combinations that are going to come as we go further in our discussion. So, at this particular moment, what we have therefore is the 2, 2, 2, where we have a two-fold axis, a two-fold axis and a two-fold axis. In case of 3-dimensional space, if these three-fold axes are three two-fold axes are present simultaneously intersecting at a point, the requirement is that these three now define 3 directions, and these directions now are with respect to each other and 90 degrees with respect to each other. They have to be with respect to each other. So, that means to say that there is some amount of restriction on the nature of the lattice which you are going to generate based on this. There is an angle of 90 degrees between 2 and 2, 90 degrees between 2 and 2, 90 degrees between 2 and 2. The combinations of with the other rotation axis 3, 4 and 6 with 2, 2, 2 with 2, 2, 2 is possible. So, there are 4 possible rotation combinations which we can think of, and they will give rise to the 90 degree angle between 2 and 3 in case of 3, 2, 2, 90 degree angle between 2 and 3 and 60 degree angle between 2 and 2. Now, I want you to digress your mind and go back to the in your notes, go back to the Escher's diagrams And in those SS diagrams you will see the relevance of 60 degrees if you are looking at 3-fold axis. You will see the relevance of 45 degrees if you are looking at 4-fold axis combining two other 2-fold axes. In fact, in the diagram which we showed, which related the lizards together, we had the indication of both the 4-fold rotation as well as the 2-fold rotation. So you have to just go back, digress your go back a few classes and see how those diagrams are so relevant for the understanding of the combination of symmetry axis which we have just now discussed. Apart from these 4 combinations, only other 2 combinations permitted under the Euler's scheme. That means the Euler's rule has to be followed. That means the P has to come back again itself. So if we go and operate some rotation axis and go to Q, Q to R, then R to P must be repeated. So if you put that condition, no other combinations are allowed except 2 other combinations which gives rise to 2-3-3 and 4-3-2. There are other combinations like N if there is an n-fold axis, but remember we are restricted to 1, 2, 3, 4 and 6 only because of the translational periodicity. So because in the crystalline state only 1, 2, 3, 4 and 6 are allowed, crystals cannot have any other combinations other than these 6 which are represented here. And therefore the 2-3-3 combination and 4-3-2 combination give rise to these kind of angles. You notice that these kind of angles look very scary to you in the beginning, but then once we get a hang of it, you will see that these two represent the octahedra and the tetrahedral arrangement in cubic systems. And we will get a better look at this as we go along. But at this particular moment, please note that Euler's theorem has to be validated, and we in this particular example which we have shown as combination of symmetry axis, we have considered only the proper axis, and there are 6 possible combinations of these proper axes, and those are illustrated with respect to the angles between them. So the angles between them also get restricted. That means the nature of the 3-dimensional lattice you are going to get, or the 3-dimensional unit cell you are going to get will be the same. It cannot be more than these types. Remember that as we will go further to the next slide. In fact, this slide is almost immediately relevant. We have illustrated here the 2-2-2, how the 3 90-degree angles come with respect to each other. So if you look at 2-2-2 here, the angles are 90 degrees with respect to each other. The next slide is shown here, the 2-2-2 orientation. You see that the 3 are oriented at 90 degrees to each other. You see the relevance of the presence of the 3-fold axis in terms of the 60-degree angles, because you now get 1, 2, 3, 4, 5, 6, a hexagonal arrangement of the points on which the point group operation occurs. Similarly, the 4-2-2 and the 6-2-2. As I mentioned, the relevance of the axis with respect to 54 degrees and some minutes and some seconds, and all that issue will tell us about the arrangement of the symmetry axis, which is shown here. At this moment, we are not going into the detail of this discussion, except to tell that it is not necessary in a crystal lattice. If you have A, B, C directions, it is not necessary that the symmetry should be restricted to those directions. The symmetry axis can be anywhere. So these, for example, in this case the symmetry axis is not along any given, in this case it is along the given axis, this axis, the 2-fold axis. But you see that the 3-fold axis is along the diagonal, and in fact 3-fold axis along the diagonal is a condition that is required to have cubic symmetry. And therefore the symmetry decides now how these the proper axis should be oriented, how the improper axis will be oriented in case there is improper axis. So we have to therefore consider not just the PPP, but we have to consider the possibility of improper axis also as combinations in the Eulerian case. So for example, if there is a proper axis and an improper axis, the first one is a proper axis, the second one is an improper axis, the third one must be improper. It cannot be another proper axis. So there is no PIP possible. That is because once we have a proper and an improper axis combination, let's go back to the previous slide. Once we have a proper and improper axis combination and we generated an improper axis as a consequence. So suppose we have a 4 and a 4 bar, the third axis should be improper. So the combinations therefore get restrained to PII IPI and IIP. So, these are the things which essentially restrict to 4. So, 4 possibilities are there: PPP, PII, IPI and IIP, and these combinations therefore are illustrated below. And this now define the remaining part of our point groups. See, remember we had 13 plus 13 point groups, proper, improper and proper, improper combined, that gave to 13, and we have to now reach 32, which is the 32 point groups that are allowed in crystalline materials, and therefore we have to have these combinations. So, if you have all proper combinations, as we saw just now with respect to the angles, which are these, the 6 of these. So, we will give rise to 6 of those. Now, the requirement that it has to be a PII combination will generate these 6. It so happens that all these 6 are not independent of each other, and in fact, for that matter, the 2 3 bar will generate a system which is 2 by m 3 bar. So, here you see that all these 6 are again degenerate. They are different kinds of point groups. These 6 are a set of point groups, these 6 are a new set of point groups. That means 6 plus 6, now 12 point groups additionally to the 13 we have already seen. Now, these are independently generated point groups, and therefore, these combinations will have to find a place in the crystalline systems which we are going to have. So, this is the reason, this is the basis of why there are different crystal systems. If there was no differences in the crystal systems, we would not have had these combinations. Now, these combinations therefore decide how our lattice should develop into different crystalline motifs. The so called 7 crystal systems, which you have studied in starting almost from your standard 12, is a consequence of this. So, you would have never asked this question in school, that when the teacher said there are 7 crystal systems, you believed it like, well, God is there, right? And then we never asked any questions. Now, the 7 crystal systems come as a consequence of the presence of the point groups and the combination of these point groups in 3-dimensional space, which obeys periodicity. So, it's very interesting. Crystalline state therefore is the most interesting way in which we can study the objects, because now the objects are kind of restricted. It is like, in a class the students are all sitting in their respective places, and we get them arrested in those places. So, their attention comes to you. So, the attention, if we want to get of the students once the class is over, is almost impossible. So, when they are restricted to those positions, these positions which are restricted will generate the so called point groups, and the presence of the satisfaction of the periodicity is a fundamental requirement, and that induces the possibility of 7 crystal systems. So, the 7 crystal systems and 32 point groups now are very easily understandable in terms of the requirements of symmetry which govern the periodicity in the given system. So, this is the state at which we see that we do now start getting the information on all possible point groups. Again, to define the point group, you should remember that the point group has this condition, that if you have a point on which you operate this symmetry, the repeated operation of the symmetry should bring back the same point, and unless that happens, you can't call it a point group. Putting that condition, and also the condition that there is periodicity in the lattice, that is A repeats along the A direction, X direction, B repeats along the Y direction, and C repeats along the Z direction. We have these restrictions of having 1, 2, 3, 4 and 6. So, 1, 2, 3, 4 and 6 will give rise to the possible crystal systems, and then the combinations of these with respect to PPP, PII, IPI and IIP will give rise to the other crystal systems. So, the direct crystal systems which we can get are the orthorhombic, the trigonal, the tetragonal and the hexagonal systems, and then these two now give rise to the cubic system. If none of these symmetries are there and there is simply a one symmetry or a one bar symmetry, that defines the monoclinic system. And in this, therefore, the case where there is two-fold symmetry or mirror, it defines the triclinic system, correction. And in case we have the mirror plane or the two-fold symmetry, it defines the monoclinic system. So, therefore, we have 7 crystal systems, the triclinic system representing 1 and 1 bar, the monoclinic system representing 2-fold, mirror and 2 by m, and therefore, these things which we say now 1 and 1 bar belong to triclinic, 2 mirror and 2 by m belong to monoclinic, and then 2 mm belong to the orthorhombic and so on. So, therefore, we have the orthorhombicity, the triclinic, the trigonal nature, the tetragonal nature, the hexagonal nature defined in these cases, and then the cubic symmetry, which is what also referred to as the isometric system, because this system does not have any restrictions along given A, B, C directions. Now, since there are no restrictions along given A, B, C directions, we will see what kind of restraints we can put to define these 7 crystal system as we go to the next class. So, at this moment we will stop at this particular point and go over to the next class.